Welcome back, everyone, for our last day of the Exposome Data Challenge. Today we have our last session chaired by Xavier Basagaña. He's a biostatistician. He's done great work in Exposome project up to now, working with epidemiologists, and I'm very excited about this last session. Don't forget to vote. So the vote for the previous session are closed now, but please vote for this last session, and we will close the vote during the discussion time, so we have time to sum up and make a conclusion about it. We're also going to make the link of the previous talk available as videos through a YouTube channel, and the slides will be next week uploaded on the event website. Okay, if you have any question, please use the chat. Xavier, the floor is yours.
Thank you, Leah. Yes, so thank you. It's very nice to see many of you still here in the last day of this workshop. Today we have a lighter session. Only have one session with 4 talks. Then we'll have a break, and don't forget to come back after the break, because we'll start talking about the next steps, including potential publications, and also importantly, we'll have prizes for the best talks. So make sure that you are there. So today's session, we call it other methods, either because the presentations touched on topics that have not been covered by the previous presentations, or also because some of the talks were related to the presentations on the other days, but we didn't have enough space to fit all of them in one session, so they are here. So we have ahead 4 very exciting talks today. I'm not sure if the first presenter is already in, because
the person is in. Yes.
Yes, I am.
Okay. Yes.
Hi.
Michele is here. So we'll start with Kim. Remember that each session, well, speakers have 12 minutes. I will let you know when you have 2 minutes left, so you can prepare to finish on time, and then we'll have some 3 minutes for questions. And remember that also at the end we'll have a general discussion. So Michele, whenever you want. Thank you.
Okay, now you should hear me, right?
Yes.
So let me go back to the beginning. Okay, let me start everything. Fine. Okay, so hi everyone. My name is Michele. I'm from Italy, but I'm here at Duke University. I'm a postdoc with Professor David Dunson. In my recent work, I have primarily focused on geostatistics, and today I will try to convince you, maybe, hopefully, that some of the most recent advances for big data geostatistics can be applied to the analysis of exposome data. So let's start. First of all, I will take a somewhat more methodological perspective here, but I will try to touch on many of the topics that other presenters have been mentioning, especially during the first day, I think. So as you see here, I'm mentioning that the exposome data is essentially quite special. For example, we have seen that there's many correlated exposures, and they may have like a joint effect on the outcome. But then we also have multiple outcomes, and then those are maybe related to each other. And so exposures, we may think that they will affect them similarly. And then when we look at the covariates that we have, or the confounders, some of their values are missing, and we should deal with that too. And finally, we have some data size that our data size is quite large. And so we would like to take advantage of all of the information that we have available. And for these reasons, we may prefer methods that are flexible, interpretable, can quantify uncertainty, and that work with big data on big data sets. So first of all, let me start with considering the model that I think we've seen in some previous presentations. We have an outcome Y, the exposures X, and then the covariates Z. And we model the effect of the multiple exposures on the outcome by giving them the underlying function H, a Gaussian process prior with some kernel K that we can choose whatever we want. And this is like what the Bayesian kernel machine regression, BKMR, does, if you're familiar with it. The problem with this is that this model is not perfect. And so first of all, we're only looking at one outcome, and then it also assumes that the values of both exposures and confounders are all available. And there's a Gaussian IID assumption on the errors. And then we also know that the Gaussian process does not really scale to big data. And so if we try to address the first issue, so we now have Q outcomes, we can just write the same model like Q times, and then everything is now specific to each outcome. But one issue with this is that this will not recognize that some of the outcomes are related to each other. For example, in the exposome data, we have a couple of BMI indices. In the exposome phenotype data, I think the name was called. And clearly, I mean, we may presume that some exposures will have similar effects on these outcomes. And so we can rewrite the whole thing in a more compact way. This also shows that the outcomes are disconnected to each other. And then basically the idea here is that instead of having an identity matrix, we can then replace it with an A matrix here, which is not an identity anymore. And it gives us linear combinations of fewer K instead of Q. We have now fewer factors. Each one of the factors H is modeled as a Gaussian process. And of course, I mean, as I mentioned, K can be less than the number of outcomes. And so we have some dimensionality reduction. This is a common method for dimensionality reduction. So let me give you an example of why we care about this, this methodology, this model. Suppose we have just one outcome, so simple case, and then we also have one covariate for some reason, you know, simple. But suppose that this covariate has some missing values, and let's call this covariate J star, like the index of this covariate. And then we relabel this covariate as our new tilde outcome. It's a new outcome now in our model, and we write it as a function of the inputs. Then our original outcome is the second one here in the list. And then it will include the effect of the original, of what used to be the original covariate. And it's just the same as the univariate model that we were considering earlier, but now we can use the first equation to impute the missing values. So this is an example of how to use this. And again, this has a compact form, and you can see that this is the A matrix. And so, you know, it's the same model as before, just a special case. So in general, we have this model. We have Q outcomes, as I mentioned. This is nothing fancy. And here we're making a simplifying assumption, as you can see from the error term, that all outcomes are Gaussian, but we don't really need this. And actually in the exposome data, I will not do this, but you know, it's just simpler to explain. So the problem with this model is that it's difficult to compute. The effective dimension is NQ, N times Q, so the N number of subjects and Q outcomes. And this means that with a standard Gaussian process, just a little more data leads to a big slowdown in computations. And so what people have come up with, for example, when implementing the BKMR package in R, is to use so-called low rank or predictive Gaussian processes. And let me mention that one of the main papers introducing predictive Gaussian processes by Professor Banerjee was mainly focused on geostatistical applications. So the same thing that I've been working on so far. And the issue with those predictive processes is that we need to choose knots, and then we want the number of knots that determine dependence to be as large as possible, but computations get a lot worse when we choose it too large. And so instead, we can do this other methodology that I'm gonna consider now. In geostatistics, we have moved along after the predictive process. And now, you know, let's talk about this that I've been working on last year and has been published on JASA. It's called the meshed GP, meshed Gaussian process. This method requires to partition the spatial domain. So for example, see here in the figure, we have locations that, where we have observed data and we partition the domain. And this is a spatial domain. And then we assume that we want to have like a directed acyclic graph that determines how the spatial dependence is going to flow in the domain. So we put these directed edges. This is a visual representation. And this is very successful in geostatistics, this methodology, where basically our inputs, our exposures, they would be, have dimension 2 or 3. And with spatial data, we can make this work for even tens of millions of observations. It's not uncommon to have millions or more. And we can make it work for multivariate outcomes. Maybe they're of different types. Some are count, some binary. They're misaligned. It's quite flexible and it works in many cases. The basic idea, more technically, is that we move from having a huge multivariate normal density of like with a covariance matrix that's like millions by millions, to having a product of conditional Gaussians. And the terms in this product are determined by the graph or mesh that we have fixed. And there's other methods that do kind of similar stuff, but I'm not going to mention those right now. And the point here is that we choose the graph or the mesh that is nice in some sense. We want it to be nice. And clearly you'll be asking here then, but why do we care? We don't have 2 or 3 exposures. And in fact, I mean, yes, I agree. And the point of this presentation is to show that we can actually extend this to more than 2 or 3 exposures. And so here I introduced the spatial meshing approach on projected inputs. And so pi meshed GP. The idea here is that we don't have data that are geolocated, and so we don't have a spatial domain, but essentially we make one just for the purpose of getting the computations to go faster. So we have the inputs or exposures or the covariates, we can do that, and we project them into a small dimensional domain, like dimension 2 or 3. And perhaps we can use PCA, but we can also use other methods. Then once we have the new small dimensional domain, we just partition it and create the mesh as we did this in the spatial case. It's just the same thing. And then we build the mesh GP, the same way. And then notice here, I need to focus on this, that the kernel does not depend on the PCA projection. This is not a single index model that I've seen. We can potentially, but this is flexible. We don't have to have any restriction on the kernel. And so now I'm going to move to some results in the last 3 slides. On the exposome data, so again, here I'm mentioning the model, and here is essentially, I'm doing it on 7 outcomes, of which 4 are actually covariates, but in the original data, the covariates had missing values. And so now we're moving them as outcomes. And we have the correlations once we consider the effects of exposures and the covariates. And for example, it makes sense here. We see there's like an overweight variable outcome and then a z-BMI, the z-score of the BMI, and they're correlated to each other. Makes sense. They receive like a similar effect. So we are saving some of the information, we're borrowing information. And let me also mention that basically 2000 iterations of the PyMGP code took about 30 seconds in the multivariate model with 7 outcomes. And BKMR doesn't do multivariates. And in the univariate case, BKMR took like about 32 times more. And this would imply that an analysis that takes BKMR 1 day would take PyMGP less than an hour to complete. Because you can see one outcome, it just took 6 seconds. And this is fully Bayesian MCMC posterior sampling. So that means that we essentially have the same kind of output as BKMR and more, but the same, so not less. Here's, for example, a figure that visualizes the effect of the confounders, or how they're associated to the outcomes. And then what I would like to show, but I haven't coded in the PyMGP code yet, is the response curves, like to the exposures. And those are built using these values, these parameters. I don't have them yet, but it's a work in progress, let's say. And these are the estimated kernel parameters, which we have because we're estimating them. And yeah, I mean, that's essentially it. I hope you liked the presentation. I hope you like spatial meshing. Hopefully I've convinced you. As I mentioned, at its core, this method is based on recent advances in geostatistics. And here I'm just listing a few of the papers that I've been working on geostatistics, but it's the same stuff. And we also have one in the pipeline here, a melange, in which we clarify how the computations work when the outcomes are not all Gaussian. And the PyMGP article, let's say, will follow. Thank you.
Thank you very much, Michele. So if you have questions, you can write them in the chat. For the moment, I haven't see questions there. I have a question myself. So you incorporate the different outcomes in the same modeling. So have you tested if there is a gain in statistical power by examining the outcomes jointly compared to doing models separately for each outcome?
Well, I have not. This is just preliminary work on the exposome. I mean, the exposome was essentially like an excuse to code something different and interesting. And yes, technically it could be possible. And I would expect that see the number of factors, you can choose it as less than the number of outcomes. If you choose it as the same, there's just going to be a matrix that's going to be Q by Q, in which you're basically just finding the correlations between the outcomes. But clearly, I mean, there may be like, if the outcomes are really independent of each other, you're going to see that matrix is essentially diagonal. So, the model can be used to essentially figure out whether it was worth using the multivariate modeling approach or not. So it has like you can do post-processing of the model and see whether it was worth your trouble from the posterior distribution.
Okay, thank you. We have a question in the chat. So it says incredible time gains compared to BKMR. What are the costs or limitations of using the meshed method? So
that's a very good question because it is currently the thing that I want to, it's going to be the core of the article when I write it with my co-authors, because essentially, so let me just make a comparison here. So in the BKMR code or method, when you have a lot of data, you have to choose these knots. And so these knots are chosen in the exposure space. The exposure space could be high dimensional. And so it may be difficult to fix the knots in a high dimensional exposure space. So that's the problem with low rank methods in high dimensional spaces. In the meshed case, there's going to be the influence of choosing the projection. So the projections is clearly because then we have to partition the projected domain. So in PyMGP, it's I still don't know exactly what the effect of the projection is, but basically the idea is that once you project the data on this small dimensional domain, you essentially end up with a model that has knots, just like the BKMR one, but the number of knots can be chosen essentially as much as the data size. So if you have 1 million observations, you can choose 1 million knots, and it's going to work. So it's different. And, if anything, if the spatial results are anything to go by, the meshed method is a much better method than low rank methods. It can be argued that in lower signal to noise data, like maybe the exposome compared to spatial statistics in which we have images, it may be argued that the difference is going to be smaller, but the time gains are going to be there. So in performance, I would expect them to be similar. Time gains, yes, it's a more modern method. So I would, yeah.
Okay.
Thank you.
Great, very nice work. We'll be following your developments. So thank you, Michele.
If I can mention, so I have not published the code for this, but I have submitted the package for the Exposome challenge. So you can actually try the whole code that I just did. It needs compilation. The GitHub repository for the spatial stuff is not public yet, but you know, it's like a preview.
Okay, thanks.
Thank you.
Okay, so we'll move to the next presentation, which is by Sanjib Basu from University of Illinois, Chicago. Sanjib, whenever you are ready.
Thank you, and can you hear me?
Yes, that's all okay.
So thank you, and thank you for this opportunity to present in this Exposome challenge. So this is going to be quite different from the previous talk in the sense we're going to use maybe a different set of methods. This work, as this slide shows, is a group work. So I am Sanjib. I'm a professor in University of Illinois Chicago in biostatistics. And this is joint work with two of my colleagues, who are Chen, who is speaking right after me, and Mary Turek. And also work of two graduate students who are on the left, Ruijie Chen and Yu-Che Chang. Also, I want to acknowledge greatly the work of Jiyoung Jang, Dr. Jiyoung Jang, who graduated, but most of this work comes from her PhD dissertation. So let me first also acknowledge the support of a grant from US National Institute of Environmental Health Sciences, and all of us are part of the group who is working on this grant. So I'm going to focus on two separate aspects in this presentation: the missing data pattern and the exposure selection. There are two kind of separate set of methods which we use to look into this. Because of the time limitation, I'll probably be very skimpy on the method side, but I'll try to say something about those methods. So as I mentioned, that this is part of a group work funded by the National Institute of Environmental Health Sciences, and this is the group who are involved in this work. We have 3 biostatisticians and 3 environmental epidemiologists who are involved in this group project. So I think the previous speaker alluded to this. We are looking at the Exposome data, and in a broader context, the setting of environmental mixtures. So these are pollutants in the environment who, as a mixture, affect health outcomes. So there are many challenges when you look at these kind of setting. In terms of the challenges that come from the statistical methodology side or data science side are the missingness pattern that we see in the data. Also, there are strong correlations associated with among the exposures. So that's another question. And then how do we select, or do we select among the pollutants in this model? So I'm going to focus on these first 3 points in this presentation. So let me start with the first point, which is the missingness pattern that we see in the Exposome data that's in this challenge. So there are 2 sets of data, one set of data without any missing values and another set of data with missing values. It's not clear how the data without missing values is created. Is it imputed or otherwise? And if we look at the data with missing values, we see that there are no missing values in the Exposome, but there are missing values in the covariate, and there are a few missing values in the phenotype measurements. And primarily the largest amount of missing value is in this weight gain variable, where we have about 10% missing data. And if we do a simple plot of this weight gain data and look at the values which are available in the full data, without the missing data, and compare that with the data with missing values. So those are these red values. So it's also not clear how these values are created. It seems that these are some systematic method is used to create imputation of these missing values. So if we dig into the missing data literature, and we have recently done some work on this. So one of the broad concepts that's used in missing data literature is this idea of missing completely at random. And many statistical methods work under missing completely at random setting if other things are met, not globally, but if other conditions are also met. And the broad definition of missing completely at random is if the missingness pattern, which I called here as R, if that doesn't depend on the data Y, then that's roughly called missing completely at random. And the Y may include the observed part of the data as well as the unobserved part of the data. There is some discussion on this definition, even though this definition goes back to Rubin's work in the 1976 JRSSB article. The distinction is between, do we mean only the observed missingness pattern when we talk about this, or do we mean both the observed as well as the unobserved missingness pattern? If we mean the latter, that has been labeled as missing always completely at random. And there is quite a bit of confusion in the literature about some of the articles, whether they refer to missing, realized missing completely at random or always missing completely at random. So we recently developed a test, a diagnostic test, to check for missing completely at random. This diagnostic test, I cannot get into the details because of the time restriction, but it's scalable. It can apply to higher dimensions. It can work with a large amount of high dimensional data. And this looks at realized missing completely at random rather than always missing completely at random. So when we applied this diagnostic to the missing data in the exposome, we see that it fails this diagnostic test. So there are issues with how the missing values appear in this data set. What happened?
We lost your, okay.
Is it back? Okay.
Yeah, is it coming back? Yeah.
Okay. So again, combining looking at the data without missing values versus the data with missing values, we see that there is substantial difference if we look at marginal correlation. Here I'm looking at the outcome of BMI, and there are differences, substantial differences between these two data sets. We also see that in terms of selection, the marginal correlations at least are not sparse. So the sparsity assumption, at least looking at the marginal correlation, we may consider if that holds or not. And again, we see that when we look at the data with missing values, there is kind of a few correlations which are positive correlations which are very high, but then there is a whole bunch of negative correlation. And then in the imputed data, there is this large range of correlation values. This is the correlation plot. I think we saw this in the previous slide also, but I want to point out that there are substantial differences in the correlation plot between the complete data versus the data with missing values. So I want to focus on some feature selection methods with highly correlated exposures, because this is a common problem in the exposome setting. So of course, there is elastic net, which combines the lasso penalty with the reach penalty. But there are various other works that have been proposed in the literature looking at other penalties and as well as combining that with shrinkage of the features. The plot on the right shows the different types of restrictions that these penalties impose. So we proposed a method. This is a work with Jiang Zhang, which addresses this question in an iterative way. So in this approach, there are kind of 3 different angles that we're trying to address. And the approach works by looking at correlation learning with the outcome, as well as correlation learning within the exposome measurements. And the third step is exposure selection. And the method iterates between these steps to address these questions. And it has a goal, these multiple goals. It's not only trying to do well in the feature selection, but it's also trying to do well in the prediction and estimation also. And we have done a large amount of simulation.
2 minutes.
Okay, thank you. A large amount of simulation study to study the properties of this method. And we compare some of the existing methods with this. So this briefly shows some of the performance comparison of this method. The extreme left-hand side is the one that we are proposing, and we compared this with various other methods in terms of prediction errors as well as estimation errors. So for the small time that I have left, let me focus on the application to the exposome data set. So there are lots of funny things that happen when you apply the methods in this exposome data set. So when you apply this to the data with no missing values, for example, elastic net selects all the variables, all the exposome features, whereas lasso select 51 features. And again, this differs between when we treat the data with no missing values versus the data with missing values. There are substantial differences about how the methods compare. When we apply our methods, we already saw that there may be lack of sparsity in the data. So in both cases, the method selects about 70 features. It doesn't reduce it further. And if we look at the intersection of those two, we see some of these features that are showing up in the intersection. So I have some further thoughts on this, but because I'm almost out of time, I would also mention that we have extended our method in the setting of a non-continuous outcome. In the GLM setting. So to wrap up, I think I'll mention that that missingness is a problem, and we have applied this diagnostic test for missing completely at random to this data, and this method is scalable and can be applied to both continuous as well as categorical data. And for feature selection and addressing the collinearity, we applied this method called co-learns, and in our evaluations, this method performs superior to some of the other methods. And I will stop there. Thank you.
Thank you very much. If you have questions, you can write them in the chat. Otherwise, well, I'll start because maybe I don't know if I got it right, but you mentioned that there were no missing values in the exposome data, right?
There were two different data sets, right?
Yes.
Yes. Yeah, there is no missing values in the exposome part of it.
Yeah, so that, yeah, sorry, because that was probably a mistake, because indeed there are missing values in the exposome data, and probably when we prepared the data sets, we didn't include the right set. So yeah, for some of the exposures, there are substantial missing values, and there are interesting patterns. So yeah, I'm sorry that we didn't include the right one that probably would make this even more interesting. But we are happy to share it afterwards in case you want to try it with the data with missing values also in the exposures.
Sure, I mean, I'll be happy to try that. Thank you.
Okay, then oh yeah, so you were asking about how the data was imputed. Yeah, the data was actually imputed. So we used multiple imputation by chain equations, but we only provided one imputed data set.
Okay.
This is how we did it.
Yeah, this was this is not behaving, but so that plot was interesting. That when I looked at the kind of the imputed values versus the rest of the data.
So I have also another question, if there are no other questions from the audience. So you mentioned this test of missing completely at random. But then there are many techniques that work under missing at random, right?
Yes.
Also, for example, we have been using multiple imputation in some of our analyses, and if missing at random holds, still we are expecting that to get to the right solution. Is that correct?
That is correct, but the motivation for developing this test, because this was kind of developed in a different, was that, yes, among statisticians and a group of epidemiologists, and a group of epidemiologists, we have, I mean, we can use missing at random, but if we look at the large users of statistics, then still people use methods which holds under missing completely at random. So that was the motivation of developing the test for missing completely at random, and also that it applies to both to a mixture of continuous scale as well as categorical scale data.
Okay, thank you very much, Sanjib. We have to move to the next presentation.
Thank you.
Which is by Chen from the same university, I think, the University of Illinois at Chicago. So whenever you are ready.
Hello, everyone, and thank you for coming. And I'm Chen, and from University of Illinois at Chicago. And my talk here is about estimating the exposome and the overall effects. We have so the exposome data we have basically is like summarized in this table. We have several outcomes and lots of exposures and covariates. And one of the problems with this data set is that we could potentially have very weak effects, and variable selections may not be able to capture them. And also we want to know after the variable selection whether we actually capture the overall effects, or we have missed quite lots of them. In the analysis, I will try to answer this type of question, and I will use two outcomes to show our method. One is the both weight, the other one is IQ. And we can apply the same method to other outcomes, but that's basically what I'm going to do here. So first of all, I applied the ordinary variable selection forward variable selection under the linear model, and for the both weight, if I exclude the covariates in the selection, then we end up find several variables here that give us significant results. And if we look at the adjust R square, we find that those variables only explain about 6% of the total variation of the birth weight. So if we including the covariates and do this same thing again, then we find we select quite a few of those covariates. And then overall, those variables explain about 38% of the variations of the birth weight. So one of the questions we have here is whether, these select models actually, capture most of the effects related to the outcome, or we have missed quite a few of them. We did this same thing for the IQ. Basically here we take log of IQ, and then we find for IQ there are lots of different exposures are related to the outcome, and overall those select variable explain 18% of the variations of the log of IQ. So if we including the covariates, it turns out that we almost select quite similar number of variables, and the explained variation is still 18%. If you recall, for the birth weight, the including covariates and not including covariates, they have a big difference. Not including covariates, about 6% variation were explained. Including covariates, we boost this percentage to like 38%. So after this kind of variable selections, we have quite a few questions. One of them is, as I mentioned earlier, did we miss any important combined exposure effect? Because the weak effects, possible weak effects of those exposure variables, we kind of worried whether we have missed, some of those very small effects, but they could be numerous such effects. We are not quite sure whether we missed them or not. The second question is, we want also investigate in interactions between those variables. We want to know whether there is an interaction and how much, variation we miss to explain if we fail to including interactions in our model. And also we want to know how reliable, those explained variation we estimated based on variable selection, in this case. And so for the last questions, we want to, construct a confidence interval for the variation, total variation explained by those covariates, so that we have some ideas what exactly, the variable selection model, helped us. Okay. To answer these questions, we proposed a method to estimate the explained variation for a group of variables. So this method allows us to select a group of variables and estimate their overall effects, overall effects in explaining the outcome variables, the variation of the outcome variables. So to give you a simple idea, here we use this simple linear model to explain the situation where we have p covariates, and those covariates may correlate. And we define a explained variation of those covariates, expand the variation of the outcome explained by a collection of covariates or exposures. So in this definition, we didn't including additional variables, but we can also including additional variables and just look at a subset of those variables and how much variation explained by those variables. This can be useful, like in exposome data, we can look at all the metals, what percentage of variation explained, and also maybe other chemicals, how much variation explained by them. So the way we estimate those explained variation is pretty straightforward and simple using these formulas. There's one important thing called weight matrix. This weight matrix can be chosen using different forms. And also for here, a set of such weight depends on a given lambda. This lambda can be chosen. All of them can work. Okay. The key feature of this method is that we can estimate the explained variation accurately without estimating individual regression coefficient, because if we have a lot of variables and individual variable effects is very weak, so it can be very hard to estimate them individually. But in order to calculate these quantities, we don't need to estimate them individually. And we can have a large number of variables in a collection. So this is different from simple regression model when the number of variables close to the the sample size, it can not work anymore. But we also allow the number of variables exceeding the sample size, but we need to supplement this exposure data. We don't need to have outcome for those supplement data. And we can also construct confidence intervals, which give us better idea of how much variation is explained. So here is an application of the method to the data for the birth weight. If we including overall all the covariates and all the exposome data, we find that explained variation is about 38.3%. Remember, in our select variables, it's almost the same. So that gives us a good indication that our select models performs quite well. For all exposome data, without those covariates, it explained like 7.4%. So our select model explained 6.1%. So it's also pretty close. But all covariates, you can see they are quite large amount of variation explained. We also get the confidence interval for those numbers, give us low bound, up bound, a better idea how much variation those estimates are. For the IQ, if you look at this, you will see that the exposomes explain quite substantial amount of the total variation explained by the covariates. But the covariates explain relatively little for those. So it basically says all those exposome can be quite important in this in determining IQ. And also we can look at individual groups of those variables, like all exposome, all metals, and all lifestyles. So for birth weight, you can see that they are very close to zero, and almost no very small amount of those variations explained by those variables. But for IQ, it is a different story, and for all exposures, you can see that substantial portions of variation explained by all exposures. So this gives us some ideas that where to look at, those variables that explain the outcome, and also for all the metals, all the chemicals, lifestyles. This give us, a good idea, how they are behaviors in those models. And also we can
we should wrap it up with you should wrap it up.
Okay. I'm almost done. And we look at the interactions for birth weight and for adjusted outcome. They are all close to zero. And also, if you look at the upper bound of the confidence interval, they are very small. That gives us some assurance that the interactions are relatively small in those data sets. And this is also for IQ when we adjust. So it is a somewhat stronger, but still because of the data limit of the number of interactions and the sample size. So we end up cannot detect them here. So here give you some ideas when and how to apply our method. So since I don't have much time, I will skip this. And here is where you can find, if you want to try the method, we have program there. It is very fast, like in a split second, you will get the results. And we would like to thank the support of our team and funding. Thank you for your attention.
Thank you. So went a bit over time, but I don't know if there is a burning question. Yeah, if not, we will give the questions for the discussion part, and we will go to the last presentation. So yeah, please, if you have questions, you can write them in the chat, and we can address them later. So the next presentation is presented by Charlie, Roscoe, and Harry Iyer. They are from Harvard University. Yeah, so please go ahead.
Thanks. Hi, my name's Charlie Roscoe, and I'll be presenting today with Harry Iyer, some work that we did with colleagues Hoi-Chi Lee and Marcia Pescador-Jimenez. Our work was on air pollution and childhood cognition, and in our approach, we used g-computation to assess mediation by a mixture of metals. Next slide, please. Okay. So first of all, a little bit of background. Exposure to poor air quality can have adverse effects on the brain, including suboptimal cognitive development in children, although the mechanisms remain unclear. In parallel, we know that some metals such as lead cause problems with cognitive development. So mediators of the association of air pollution and cognition, which can include metals, are often individually assessed rather than as co-occurring mixtures. So by understanding a metals mixture as the mechanism of the association of air pollution and cognition, we were hoping to be able to inform strategies targeted at reducing metal contaminants in air pollution emissions. So a little bit more hypothesis driven than some of the other approaches that we've seen. For example, you might think of lead being removed from petrol due to its widespread health effects, but instead of looking at one metal, we wanted to look at a mixture of metals. So we aim to estimate the impact of reducing harmful metals mixtures associated with air pollution on childhood cognition and accounting for important socio-demographic covariates. Next slide, please. Okay, so to do this, we used the Helix cohort and we restricted to those children who had complete data. We used outdoor air pollution PM2.5 measured in micrograms per cubic meter. This was estimated at each child's residential address using the escape land use regression model. And PM2.5 was averaged for the year prior to blood draw and outcome examination. So our mediator was a mixture of 9 metals assessed from the blood draw. And this was conducted in children ages 6 to 9 years old. These metals were available on a continuous scale and we log transformed to account for a skewed distribution. So for our outcome, we used the Raven's color progressive matrices. This is an internationally standardized, non-linguistic and culturally blind computer test, which is used to assess non-verbal intelligence. It takes around 1 hour to complete. It consists of visual spatial reasoning tasks, whereby the participants have to find missing pieces in a visual display, among several alternatives with increasing difficulty. There are strategies that children can use to improve their score, including constructive matching and response elimination. The outcome is a count of correct responses, although in our analysis, the distribution of the outcome was linear. So we use linear regression rather than Poisson in our models. Next slide, please. So our statistical analysis, we have no equations on our slides. We can talk about that later. We applied causal mediation analysis and quantile g-computation to estimate the proportion of adverse effects of long-term PM2.5 exposure in childhood on Raven IQ score mediated by blood metals. So step 1, we produced an outcome model. So we estimated the association of long-term PM2.5 on the Raven score. We used multiple linear regression and we adjusted for socio-demographic covariates. Step 2, we produced a mediator model. So we estimated the association between the metals mixture and the Raven score. To do this, we used quantile g-computation in a linear regression model, and we adjusted for socio-demographic covariates. We used quartiles of each metal component in the mixture. So each metal in the mixture was split into quartiles. Basically what this method does, looks for the joint effect of the metals in the mixture acting together. This approach reduces the number of required mediator models whilst incorporating multiple highly correlated mediators. Next slide, please. Okay, so this is the bulk of what we will get into. So we estimated the controlled direct effect of PM2.5 on Raven score after lowering metals mixtures. To do this, this is where like the causal mediation comes in. So we estimated the potential benefits of lowering those metals whilst we held the air pollution levels constant. So we estimated a counterfactual mean Raven IQ score had everybody been exposed to the 25th versus had everybody been exposed to the 75th percentile of PM2.5. And we estimated the controlled direct effect fixing the metals mixture to the lowest quartile for all metals in the mixture. And we use standardization and bootstrapping to obtain confidence intervals. I'm now going to hand over to Harry Iyer to present our results. Thanks, Harry.
Thanks, Charlie, and thanks everybody for the opportunity to speak with you. So we've seen a lot of these correlations, so if you bear with us, is the last one, hopefully. So we've got the correlation between PM2.5 and all of our metals. And so I want to just draw your attention to the row here, so we can see PM2.5 is correlated positively with copper, lead, and cobalt. Interestingly, is negative or null for the rest of the metals. But it's important to point out this is a univariate correlation, and so when we start to adjust for things, this changes a little bit. These are the results of the outcome model. So we're regressing air pollution and some of these covariates on Raven score. And so in the univariate case, there's quite a large decrease, about 8.6 units. And as we start to adjust for things, it goes away. Very interestingly, just adjusting for age and sex seems to attenuate the coefficient a lot more than adding the rest of the variables. But the kind of takeaway here is that sort of following our conceptual framework, we do in fact see a significant 2-unit decrease in Raven score associated with the 10 microgram per meter cubed increase in PM2.5. So now this is the result of the mediator model. So we want to understand how the metals mixture impacts Raven score in this population of children. And so when we applied quantile g-computation, we got an overall estimate of a 0.7 unit decrease in Raven score for every quartile increase across all 9 of the metals that we looked at in this analysis. And so to get some intuition on what's driving this, we see that really copper, molybdenum, cobalt, and lead are sort of the main weights, the largest weights on the negative side were kind of assigned to those metals. Copper, cobalt, and lead, as we saw in the correlation, are positively correlated with air pollution. So that, again, kind of aligns with what we sort of understood the system to look like. And then cesium and arsenic were actually pulling in the other direction. And so this is kind of where we're now applying this causal mediation framework to understand how manipulating both air pollution and metals levels starts to change the adverse effect of air pollution on Raven score. So in this first panel, what we've done is we've plotted the counterfactual mean Raven score, had all the children being exposed to the 25th percentile in red, 75th percentile of air pollution in blue. And so as we would expect, higher air pollution is, as we see, lower Raven score. And this is about a 1-unit decrease for that IQR increase in air pollution. So now we've fit a model where we've introduced the quartile dummy variables for all 9 of the metals. And so because we've added a ton more parameters, we see these confidence intervals start to get quite a bit wider. And so the result is no longer statistically significant, but we do see a modest attenuation, whereas here it was about a 1-unit change for the so-called total effect. We see about a 0.8 unit decrease when we block effectively that metal mixture pathway. So now things start to get really interesting. So here, what we've done is we've allowed exposure mediator interaction. So we've fit an interaction between air pollution, the PM2.5 coefficient, and all of the dummies for the quartiles representing the metals mixture. And so by doing that, again, we see you've got pretty wide confidence intervals, but we see these really, really stark patterns where effectively there's no real difference there's no real effect of air pollution until metals mixture starts getting fixed to quartile 3 and then quartile 4. And so if among in the sort of setting where children are exposed to the highest quartile of metal mixture, we would expect to see a 3.2 unit decline in Raven score. And just for sort of context, there's a 2.7 unit increase per age. So we just kind of looked in the data, fit a simple regression with age, that coefficient was 2.7. So this is, you're essentially losing over a year of development potentially, is what these data seem to be suggesting. And so the other interesting thing is that those adverse impacts are really born when air pollution levels are high. We don't see that dramatic decline so much when air pollution levels are low. So what's the takeaway here? The first thing is that this suggests that kind of as we kind of thought in the conceptual framework we presented, lowering metals mixture seems to really offer benefits. The air pollution effect isn't as bad, and particularly children exposed to high levels of air pollution would benefit from if you could somehow vacuum up all of the metals that we looked at here. We did encounter some limitations as we were doing this analysis, and one in particular was modeling exposure-mediator interaction. This is really important in the causal mediation framework to think about, and so we just sort of fit interactions with all of our dummies, but that's obviously not a very parsimonious approach to take, and with a smaller data set that might really not be tractable. So we've seen some presentations, I think, over the past few days that might help us think about that more, but we'd love to hear thoughts from you about how to do that. The second thing that came up was there was very high correlation between the study site and air pollution levels, and so we don't have time to show this, but some of these sites had very high burdens of air pollution just systemically, and other sites had very low. So we chose not to adjust for site here because our question is really more global. And if we'd adjusted for site, we're sort of asking a different question. We're saying within a site, how does this sort of system work? And so I think in order to tease that out, it would require a bigger data set with perhaps more sampling within a specific defined geographic area, but with varying levels of air pollution. So that's another challenge that we can talk about. But that all being said, this was a really cool opportunity to use a really rich set of data. Quantile g-computation does seem to be a nice way to make this problem of mediation tractable when you have a complex set of mixtures, and it fits very nicely into the causal inference type paradigm that many people might be familiar with. And so we applied this for our sort of cognitive impacts of air pollution and looking at the effects of metals mixtures, but you could certainly think about doing something similar for a wide set of questions. And so these are just some references to some of the causal inference literature that backed up this work. And I do want to acknowledge there was a group of us at the Harvard Space Lab that contributed to this. So Hei Chu and I kind of worked on the code. Charlie and Marcia helped us really think through the overall causal question here. And so with that, yeah, thanks so much for listening. Looking forward to the discussion. Thank you.
Thank you very much, Charlie and Harry. Well, let me start just with one comment. You were mentioning the issue of site, no, or adjusting for site, or no, and this is, I think, one of the interesting things about our study, which also makes it sometimes difficult to analyze. We have different sites that actually they are quite different in terms of several exposures. One of them is air pollution, but also diet is very different. And I think some of these metals also you can get them from diet, and there can be well, there can be issues there with some confounding by site, diet, air pollution, and all these things. So yeah, it's one of the issues that we always struggle on how to deal with that. And yeah, I don't know if you had more thoughts on how to go about that.
Yeah, yeah, Charlie, did you want to take this? I'm happy to as well.
Go ahead. I can go after you.
Okay. Yeah. No, I think that's a really good question. It's something that we've been discussing as a group. One important thing to point out here is I think the results on their own still stand if not all of the metals are sort of operating through air pollution, right? Because I mean the benefits that you see are such that I think it should really motivate potentially intervening on those different diet areas. I just wanted to point that out. That's not totally related to the comment about how to deal with site, but it's just something, again, that I think is really important to keep in mind. In terms of adjusting for site, I think we could certainly just do it and see what happens. But yeah, I guess it does become a question of sort of, are we more interested in at the level of site? Is it worth adjusting for confounding when we saw that really age and sex seems to do most of the heavy lifting to adjust for some of those other differences? And so it's just kind of a trade-off, I think. But there's no reason that we couldn't adjust for site, would be kind of the way I think about it. Yeah, and Charlie, I don't know if you have any other thoughts.
Yeah, I think from the exposure side, if you adjust for site, you're just like losing so much contrast in your exposure. It's very difficult in this cohort. And they are, I mean, socio-demographic, everything is very different in these sites. So yeah, ideally you would just away that, but you don't want to adjust away the air pollution contrast. And yeah, I'm not super sure how to get around that unless there could be more sampling, you know, in the kind of rural areas around some of the more polluted sites, or yeah, it's pretty hard.
Yeah, no, it's a complex issue, and there is always this trade-off of adjusting for confounding by site and then getting rid of the exposure contrast. So yeah. We have another question in the chat from Lorenzo. He's asking, can you use this framework to allow for multiple outcomes, like multiple cognitive impacts? And is there a limitation with several mediators?
Harry, do you want to take this?
Sure. Yeah, so let me start with a question about outcomes. So I think in the sort of tradition, if you will, when we start to apply these causal inference models, we typically like to really focus on one outcome, in part because it's really important to consider the exposure outcome relationship in the context of that particular question. So I think, you know, the example you gave, if you had multiple outcomes that are very highly correlated, you might say, well, okay, that's probably fine. If they're all correlated, you might think about coming up with some kind of a composite index maybe. But because the question and the confounders that you choose are so dependent on the exposure outcome relationship, you may end up with an issue where you might, based on the literature, based on sort of conversations with your colleagues, they may want you to adjust for some things that in one sort of exposure outcome setting that you would need to change for another one. Tyler Vanderweel has written a little bit about this, and he's proposed an outcome-wide epidemiology approach that might be sort of relevant to this question as well, that I would encourage others interested to look at. The second question was how the correlation between mixtures. And so this is certainly a very important problem. Actually, there was a really great presentation, and I apologize, I'm forgetting the name of the presenter, but it was a colleague from University of Turin who talked about this and how you often want your mediators to be temporally aligned or to sort of treat them together as one unit. So I think here, by using the quantile g-computation idea, we're reducing the dimensionality effectively by thinking about these in terms of quartiles. We are including all of them jointly, but I think if you don't have a good idea of the temporal sequence, there's not really a way to get around that, except certainly getting a bigger data set maybe. So it kind of fits, but you have to think very carefully, I think, about the timing of everything. And if they're all sort of collected at the same time, you do have to adjust for all of them, would be the way I think about that.
Okay, thank you very much. I think we'll move now to the general discussion part, which for this session is a bit more difficult because the different presentations covered different topics. But if anyone has a more general topic that they would like to discuss, please, you can write that in the chat. Well, for example, two of the presentations mention missing data, which is an issue that we haven't talked a lot, and apparently we didn't provide the exposome data with the missing values. But yeah, I don't know if someone wants to say something about how the different methods can deal with missing data. I guess some of the Bayesian techniques can handle that, but yeah, I don't know if anyone wants to mention anything on that.
I mean, this is Sanjib. I'll make a comment. I mean, in general, missing data, as you've seen, is a very messy problem. I think when you are using any kind of likelihood-based method, including Bayesian, then either you are working under a missing at random assumption, or if you're not specifically modeling the missing data component of it, the R part of it, then you're working under a missing at random assumption. Or if you're specifically modeling the R part of it, then you're specifically modeling the missing data component, and in that setting, no matter what you do, it becomes pretty much model dependent. So there is not really much way of kind of getting out of that option. So yeah, so I mean, if you mention Bayesian method, yes, if it's, and it can automatically handle that because it will impute the missing data, because it will simply treat that as a non-observable, and it will be imputed automatically from the model.
Yeah,
I'm actually a Bayesian in this talk. I'm using non-Bayesian methods.
Yeah, so Michele, your model naturally incorporate or deals with missing values in the exposures.
Yeah, I mean, I agree. Actually, yes, I totally agree. Like, in a regression setting, usually you're fixing, you're conditioning on the values of X. Like, Y is your outcome, X is your usually your regressor, and then you're conditioning on it. And if you have some missing values, you kind of have to do like a joint model if you really want to, like, model the missingness not at random. And so, you jointly model Y and the X. And then, so in my case, I mean, I was just making that as like a justification of in a case in which we may want to use a multivariate outcome model. And the justification was, okay, look, you can use this when you have missing data. And in that case, the way in which I was considering missing data to be modeled was as a function of the exposures. So even the covariates would be modeled as which is just, the data you have, you use it. But there's like, I don't know, I am no expert in missing data imputation, so I will let the experts talk. I mean, I was just making that as an example.
Yeah, I don't know if some of the non-Bayesian methods, if there is someone that can tell us how they deal with missing data in the context of non-Bayesian methods, or.
I mean, for missing data, I'm not sure if there are non-Bayesian methods. I mean, they are somewhere in between in some way, because you have to treat the missing data as random and you have to model it. So, I mean, the imputation, the multiple imputation, if you go to the next stage, it becomes Gibbs sampling or something, right? So I'm not sure if you can, I think there are likelihood-based methods and Bayesian methods, but I think just modeling, if it's missing not at random, not only you have to model Y and X, you also have to model the R, the missingness indicator. So that's where it becomes more complex, or you have to use some kind of the latent class type of model. So yes, so it's not an easy problem. But if you work under the missing at random, I think then the likelihood methods are very helpful.
Okay, I see there are no other questions or topics. I remind everyone that you still have time to vote for the presentations for this session, but you have to do it right away, because soon we will meet to make the final decision. Yes, so if there are no other comments or topics, we'll close this session here. I remind you that you should come back for the after the break for the concluding remarks, where we will start to talk a bit about what to do next, and also thinking if there can be publications out of this. And also very important, we will give prizes to the best presentations. So please come back for the closing of this event. So Thank you very much to the speakers and their teams, because I know that many times this is a team effort, and see you after the break. You have the spatial chat as well today. Yeah, yes. So you can go there if you want to. Okay, welcome back. We'll start now the session on concluding remarks. So let me share the screen. Okay, so thank you all for making it to the end of the workshop. I think from the organizers' point of view, we are extremely happy with the response to the challenge, both in terms of the number of participants who sent their work, and also the quality of those presentations. I think we have had really excellent presentations throughout the workshop. And indeed, it was truly a challenge for you, for the participants, not only because the kind of data to analyze and the methods and so on, but also because we gave a very short time period for you to do this exercise, and you needed to familiarize with the setting and with the data. And we know that you are already very busy with working with your own things. So we are very grateful that that you find the time to work on our data. Also, we have had a wide range of topics and methods. So we have to say that it has been very exciting, and we have learned a lot. So truly, thanks to all of you, especially to those who submitted their work and who presented the work here. Although we know that many times this was a team effort, so we thank all the teams. So this workshop was built around this Helix data set, and we're very proud of this data set. As with many of the projects, your projects as well, you know that there is a tremendous amount of resources, time, and money invested to finally have this end product, that is this clean data set that you were using. And on top of that, there is the generous participation of the volunteers, which they have to contribute with their time and even with their blood and other samples to this kind of studies, and sometimes coming to very long follow-ups. So I think that this is something that as data analysts always have to keep in mind where we're in front of this kind of data sets, all the work that is behind that. So apart from that, we think that our data set has some unique features that on one side, it's useful to answer some biological and public health questions, which is the ultimate aim of the project, but also I think is useful for data analysis methods development. And we kind of confirm that by attracting your attention to this data set and for you trying your methods, the methods that you developed on our data. So we'll about that. And this brings me to a reflection on data sharing. You know that sometimes it's difficult to share data for legal or ethical issues, but many times also for researchers' interest. And well, I think it's understandable that if you spend a lot of resources on developing this data, that you want to be the first to exploit the results. So I think this is understandable, but after some time, I think it's very good to share it. We did it here, even though we share the data with some perturbations. And the experience has been very positive. We see that once we share the data and different analysts look at the data, they do it in different ways with different methods, and they get really different insights, and it's a way to advance scientific knowledge. So we hope that events like this will encourage the sharing of the data in the future. So yeah, speaking of future, here we're using the data from the Helix project. This project is officially finished, even though we are still publishing a lot on this data. But we have a new project called Athlete, also dealing with the exposome, which is kind of a continuation of the Helix project. Here you have the websites if you want to visit them. And actually this data challenge event was organized within the framework of the Athlete project. So in Athlete, we have additional cohorts, we have additional time points, we have additional outcomes and exposures. We have some new cohort specificities. In the end, we have more challenges. We are very happy to collaborate with you on statistical methods to analyze these data sets. So these connections that we made through this workshop, we hope that they will continue. And certainly, if you are interested in this data or on proposing some methods, we'll be very happy to collaborate with you. So what are the outputs of the workshop? Well, we have the talks, there have been new ideas, there has been discussions, maybe new collaborations with us or between other participants in the workshop. We will also share the slides and the videos of the presentations. They are actually already on YouTube. And also we are sharing the code, or every one of you that participated are sharing your code. And this will facilitate that others use your methods, but also it will facilitate that you can use other people's methods. And a final output of the workshop, it may be a scientific publication, which is something that we would like to discuss with you. Yeah, we'll discuss that in a minute. Also, here I listed a very incomplete and selected list of remarks that we can get out of the workshop. For example, we have seen very recent innovations in the field of finding the effect of mixtures of exposures involving constraints or stratified analysis or multiple time points or interactions. We have seen actually many teams addressing the same problem and getting to similar solutions, which is, I guess, reassuring. But also we have seen that there is not a perfect match, and here there is probably a need on think about how to go about that when we have several methods to address the same question. What would be the most appropriate way to report that, and maybe do some comparison of the results of the different methods. Also, an issue that has emerged is using continuous and categorical exposures. In some of the presentations, this was not possible to accommodate that, and they only used continuous exposures. So there may be some room for extensions of the methods. Also, just picking one specific result showing that random forests seem to perform well with omics data, including multi-omics. And also, there was a lot of interest on mediation by the omics layers, but there we also had discussions on the underlying causal structure and how this can be very important for the final results of such an analysis. So, coming to the issue of publications, there has been other workshops, similar ones that actually we inspired by this kind of workshops. Some of you participated in them actually, and sometimes these kind of workshops lead to a publication with a summary of the topics discussed or the results. So this can be a possibility. We could try to write a workshop report, even though we covered many, some of them are a bit different. So we will have to see how to accommodate that. We could also think of papers on a particular challenge addressed by different methods. So, for example, many teams use BMI as an outcome, and they try different methods. So we could try to do a paper on that, on analyzing the relationship between the exposome and BMI and comparing the results of different methods, reflecting on the advantages or disadvantages of the methods, and so on. We could also think of tutorial-like papers where we basically explain how to conduct some analysis or what are the possibilities and the available methods. And also we can think, or you can think of if the work you did for this workshop you think that could be extended to become a paper in itself, then you would need to do a formal data request. Here you have the details on this website on how to do that. This is a process that also we have to follow within the members of Helix, and it's just a way to make sure that that we know that this is being done, and make sure that there is not other people working already on exactly the same thing. So yeah, if you are interested in that, please let us know. So yeah, I think here well, we can keep it at the end of the presentation. We would like to hear what are your thoughts on potential publications out of the workshop, and based on this input that we get from you today, or if you want to drop us an email in the next days with some ideas, then we will follow up with you with a more concrete proposal or on the next steps. So I'll finish while thanking the team that work on this on organizing the event. I think here it's fair to say that there is a special person who is the one who got the idea to do this workshop, the one who was pushing them to implement it, and the person who took the lead in the organization of most of the aspects, and then all the rest followed her. So yeah, I think that a big part of the success is due to Lea, and it's good to recognize and acknowledge that. But we also thank all the other members that contributed in different aspects of the organization. Also to Rodney, Yvette, and Alesh, who make sure that the communication and all the logistics work well for the event. I would like to mention that this event was made possible by different projects or grants. So as I said, this was organized within the Athlete project, which is funded by the Horizon 2020 European Commission. And it's a member of the European Human Exposome Network. Also, it was funded by the Severo Ochoa grant, which is a center that covers, for example, the organizations of workshops such as this one. And then this is also an initiative of the ISGlobal Exposome Hub. Here you have a link to the website where we make available the developments that we do around the exposome within ISGlobal. So before going to the prizes, I think I'll stop sharing here to hear your thoughts about what we can do in terms of publishing something out of this workshop. So yeah, this is now open for your input.
For discussion, I just want to acknowledge that that's some people in the general public that they don't have the microphone because it's not meeting mode, the Zoom. So they might write on the chat and perhaps I can give them the floor as panelists.
Okay. Okay, so no one is.
Well, I'd like to say something. Well, yes. Well, first of all, again, thanking all the people who participated in this workshop, because as you mentioned, Xavier, the presentations were really good. The methods and the developments were very high with a big level. I've been looking at the codes that people have submitted because, you know, I'm in charge of maintaining the GitHub, and I had a look at the codes, and the workshop is not only useful for knowing new techniques and so on, but also for having access to new packages, new tools, because actually there are people who have been developing new packages for doing their analysis. So another output of the meeting are code, libraries, packages that other people can use in other research projects. So having said that, I think that there are a couple of presentations with a very nice results, and also from a statistical point of view. And I just say that if you think that your project can be published in a paper, just send us an email and we'll help you to facilitate the real data and to reanalyze the data and to help you with the writing, because I guess you did a very good job. So I just say that please go ahead and don't hesitate to contact us if you need something else. Maybe I'm thinking also in writing a report with the main techniques and also putting your code. So I'm asking permission for using the code you send me just to create a repository saying, for example, methods for mixture of exposures, and put there your code. So if any one of you is having problems for having this visible or open source, please tell me it. If not, I will assume that if you are saying this in GitHub, this will be open. So you saw that the license in the GitHub is mid. So in principle, people can use, redistribute, and do everything with your code. So if you have any problem, just please send me an email saying that this is not possible, and I will remove this from the GitHub. That's all I wanted to let you know.
Thank you. Dania made a comment in the chat saying a paper highlighting that there is no one approach that fits all, and the advantages and limitations of novel statistical approaches presented in the workshop can be very informative. Thank you, Dania. So I think, well, if there are no contributions, also we see that not everyone was able to join now, not all participants are here. I think what we'll do is we'll circulate an email to all the participants explaining what I just have said, that we would like to get some outputs in terms of publications out of this, and maybe yeah, giving some of the possibilities, and then asking for your input, and maybe later on in a few weeks we can come back to you with something more structured, with a potential plan that we can discuss with you. Yeah, there's another contribution by Carl, maybe a graphical overview of tools to make it easy for people to find what it is that they may be interested in. Yeah, I think this is a very good suggestion. So we'll do that. We'll compile all the input we get, and we will come up with a proposal that we'll go back to you for feedback, and hopefully we can get something interesting out of it. So having said that, I'll leave the floor to Lea, who will announce the names of the winners of the prizes, and we'll close the event. So, Lea.
Yeah, thank you, Xavier. Thank you for the acknowledgement as well. Let me share my screen for the last slides. Oops, sorry. So yeah, we had two types of votes. One we called popular vote, and actually, yeah, we had a fair amount of people voting for each session, and we had one overall winner, and this is Alejandro Caceres from ISGlobal. The vote is not biased by us. We checked who voted, and it's across the different institutions. Yeah, his talk was a very original view, actually using causal random forest to determine exposure environments with high sexual dimorphism. I think it's a very interesting research question. So well done, Alejandro. And then we decided to give two prizes for by the committee. And the first one is to Glenn McGee from University of Waterloo. It was actually the first presentation, but we thought he had a very clear way of presenting his Bayesian multiple index, a very elegant way. So well done, Glenn. And the second winner Basically, as Xavier said, we had a range of tools presented, but we wanted also to acknowledge someone who had actually used and made the most of the richness of the data set in terms of also all the omics data, which is a big challenge because of its dimensionality, intercorrelation of the data, but also difficulty of interpretation of this omics data. And we thought that Chen from Stanford University did a great job by doing a mediation analysis between all the exposome and the internal omics using most of the layers and the multi-phenotype. So this was also a very elegant illustration and really going to the core research question of how omics can be used to link exposures and phenotypes. Very impressed by this work. So yeah, thank you for all the participants. And yeah, we hope this is just a start of more work together. We could think of having this regular meeting, definitely having a follow-up on this presentation and hoping for more collaboration with some of this analysis.
I don't know if we have some of the winners here.
Yeah.
If they want to turn on the camera, maybe
Alejandro is here.
Them, a virtual applause.
Yes.
Hello, everyone. Thank you very much for the prize. And well, I want to congratulate you guys who organized this. It was very exciting. And I also want to congratulate everyone who took part, because it's like a lot of work in a short time. And it was really amazing. So like, congratulations to everyone.
Thank you.
Sure. Glenn, I think is on. Oh, Glenn can turn on the camera, but he's thanking in the chat. I don't know if the other winner.
Okay, good. And I don't know if is the other speaker here?
Yes, maybe not. I think it is. Okay, well, anyway, okay. Congratulations to all the winners, and thank you for your contribution.
Okay, I think this is good to close the event, just on time too. For us in Europe, it's Friday afternoon, so we're closing a bit earlier. Yeah, I think it's actually was also a bit exploratory way to collaborate and do a conference. Initially, we're thinking, okay, let's do a workshop with professors doing presentation and stuff. And I actually thought that's a bit boring. First, we all bored to like watch people on videos and online Zoom. So how to make that a bit more interactive, how to have real brainstorming session. And actually, yeah, I found working all on the same data set in a short time, a bit inspired by hackathon from startup world, was a very good way, maybe a bit different for us academic, but we used to each work on our project. I think it's a very good way to collaborate and actually making, exposome research going further, because it does require different set of disciplines and way of thinking, from system biology, from epidemiology, from data science, and having all of us working together. I think it's a very good way on the same data set. So thank you to all participants. If someone has something else to say, please go ahead, and we will post all the videos of the event. They're actually already on the YouTube channel. Maybe Rodney can put the link. And we'll have also the slides and the code available. So the event, we want it to be to have a legacy for everyone. Thank you, everyone.